Well, good afternoon, and welcome to this semi-plenary lecture. I'm Tom Hughes. I'm from the Odin Institute of Computational Engineering and Sciences. It's a great pleasure to have the opportunity to introduce Victor Calo, whom I've known for about 19 years now. Let me tell you a little bit about Victor. He did his undergraduate in civil engineering at the University of Buenos Aires, and that was in 1998. He then came to Stanford University, where he did an MSc in geomechanics. And that was about the time he wandered over into my office and decided he wanted to do a PhD in computational science. So Victor had a very strong background in foundation engineering and geomechanics, but the only support I had was in turbulence. So he quickly converted to become a turbulence person, and he did a fantastic job in studying the problem of transition to turbulence in the boundary layer. In fact, he discovered exactly what the issue was and wrote a brilliant thesis. That was at Stanford, although physically he was located here in Texas with me. It was about the time I moved. He finished in 2004, and then shortly thereafter, he went to the King Abdullah University of Science and Technology in Saudi Arabia and was on the faculty there until 2017, when he went to Curtin University in Australia. And he is the John Curtin Distinguished Professor there. So that's his career. I'll tell you a few things about what he's been doing. He has an absolutely awesome publication record. He has about 200 publications of all kinds, over, I don't know, 120 or so archival journal publications, all since he left Texas. And that's in just over a decade. When he was my student, every meeting he'd have one good idea after another. He had so many good ideas he could not pursue them as a student. I once told him, you're going to be a much better professor than a student because you can get other people to do your work for you. And that has proven to be the case. He's really a great researcher and a great leader with a fabulous team down there. So welcome back to Texas, Victor. We're anxious to hear your talk.
Okay, so, good. So I'm going to be talking about work we have been developing mostly for the last year with Sergio Rojas, who's a postdoc in my group, and Puria Behutfar and Roberto Sier, who are students in my group, and then a lot of the mathematical proofs and the constructions were done in conjunction with Alexander Ern and Ignacio Muga. So the work basically, the idea behind what we're trying to do here started basically from my thesis work, which it was done under Tom's supervision, where basically if you have this model problem, which is advection diffusion, skew to a mesh, you put a mesh, you would like to see a solution like this. Finite elements, standard continuous finite elements give you garbage because the system is unstable. And traditional techniques such as streamline upwind Petrov-Galerkin, SUPG, relational multiscale, and things like those give you things like this, where you have some oscillations around the interior layers, and usually at corners of the boundary layer, you have higher oscillations. So here, there exist these techniques which can address this problem, but they are problem specific. So you have to learn how to discretize a particular PDE, learn how to determine the coefficients that are used in this formulation, and then use traditional finite elements to do that. Obviously, you can impose boundary conditions weakly, and then you can do, for example, least squares finite elements, which tend to basically diffuse this sharp interface all over the domain. Basically, the boundary layer starts at this corner and goes almost all the way through the other side of the corner. Again, you can do traditional finite elements, and now as soon as you impose weakly imposed boundary conditions, the solution becomes much better. Rather than being 4,000, it's just 3 rather than 1. And SUBG with weak imposition of boundary conditions becomes much better. So our goal is basically come up with a formulation that looks a lot like SUBG in the sense that you put continuous basis functions and you can obtain stable discretizations for arbitrary meshes. And in addition, we also would like to develop a method that has error control for adaptivity and hopefully develop an automatic scheme for adapting the mesh. So the way we went about it was, since I was stuck in wanting to use continuous finite elements, continuous basis functions such that you can give them to an engineer, and all the pre-processing and post-processing tools that are used in conventional finite elements could be used, what we did was we needed basically a non-conforming formulation, so we went back to the drawing board and picked up discontinuous Galerkin theory and techniques, and then borrowed from Leszek Denkovich's and Diego Palakrishnan and many people who have worked over the last decade on DPG methods, so discontinuous Petrov-Galerkin methods, the ideas of residual minimization. So we are trying to basically merge these two ideas. We are trying to build a non-conforming DPG method. That's basically the goal. Where we can, by being non-conforming, now we can measure the error norm that we use to control error representation can be stronger than the conformity that DPG would give you, the conforming DPG. And also you can use traditional bilinear forms that come from the textbooks in DG. So basically, well, this summarizes what I just said. So at the end of the day, we would like to have an error representation which has, given the nonconformity, has a strong norm to control it. And we want to use continuous continuous finite elements, basically. That's the goal. And we want to achieve, basically, and have a provably stable formulation. And the key ingredient is really the theory of discontinuous Galerkin. So in many ways, what we are doing is you can pick the theory of Ern and Germond or any book that you like on DG methods, and from there, read the norms in which they prove convergence, and the bilinear forms, you plug them into your framework, and it works. And so the schematics of idea is the following. So now we are not even trying to do a second-order method. We'll basically focus on pure advection, and we'll still want to use continuous basis functions for the discretization. And the problem is exactly the same problem as before. So we'll have an interior layer. Now we can only impose, since we have pure advection, we can only impose inflow data at the inflow, and the outflow is basically weakly imposed, and these will become basically the bilinear form by just doing multiplying by a test function and integrating over the domain, over the partition. So as I mentioned, what we did is you go to the literature and you read a DG formulation that is stable, and that would give you basically this bilinear form, the loading term, and here are the definitions where this eta that is over there would give you, if eta is 0, it gives you central fluxes. If you put different than 0, usually 1, gives you upwinding. And upwinding has a better quasi-optimal convergence, so we'll basically focus mostly on upwinding solutions. And then for these kind of discretizations in the theoretical framework, there are norms under which you converge. So if you know the SUPG theory, there's going to be some triple norm under which you converge. So something similar happens in DG, and you postulate these norms that are discrete in the sense of these are norms that depend on the mesh size and things like those. I didn't put them just to skip details. I'm going to be talking about this in more detail on Wednesday morning. Anyway, so these are the traditional jumps and average operators that would appear. So nothing really new. This is standard techniques. And what we did is basically borrowing that framework. Now what we postulate is residual minimization in the dual norm of the DG. That's basically what we end up doing. And this residual minimization is akin to the formulation of DPG or residual minimization of Damen. So there are many ways of thinking this problem. But bottom line is that with this formulation, you can just borrow directly the proof of convergence of DG and apply it to a proof of convergence of this DPG framework. And then the problem we end up solving, actually, the implementation that we do in Phoenix is this saddle point problem. So this is the inner product in the DG norm. Then the representation of a residual is this equation. And the second equation is a weak imposition of Galerkin's orthogonality. So the resulting system will look like this as an operator. So this system is always well-posed. It's symmetric, positive, definite. And since we choose a domain, we put a mesh. On that mesh, we construct DG basis functions. The solution of the inversion of this G is global, but it's equivalent to the cost of doing a conventional DG formulation on that mesh. So it's as costly as doing the inversion of a DG, typical DG discretization. And well, from this interpretation, you can use this first line that represents this epsilon to be your residual representation, and that residual representation can guide automatic adaptivity. And the resulting Schur complement becomes the stabilized continuous finite element formulation. Although, since G is global, this matrix is global. So we never construct that. We apply the operator and do. So for example, the way we are presently solving this system is we do sparse Cholesky decomposition of G because it's symmetric positive definite. The condition number is terrible, but it behaves really, really well in practice. That's one of the things we need to prove, to explain and then prove why it behaves this way. And then we simply apply that Cholesky decomposition, the sparse Cholesky decomposition here to do conjugate gradient. So we do usually 2 outer loops of solving this system, updating. Now it's orthogonal because this is just the inverse. So we solve 2 updates of this system, and we converge. That's basically the way we solve this system at the discrete level. And again, just as a note, if we write this system for a conventional DG formulation, and we choose U to be the complete space, not a subspace of the DG space, basically this becomes a redundant system, and B is simply the traditional DG formulation, and epsilon is basically meaningless because it's at the discrete level 0, exactly. So let me show you some examples of how this formulation, which we start with this mesh, which doesn't even represent the data, and the boundary data. And then we use this automatic mesh refinement to construct meshes. So, well, first we use uniform meshes to show that if the formulations are optimal, here DT means discontinuous trial, which is conventional DG formulations. And CT stands for continuous trial, which would be the continuous Galerkin formulation that this stabilized continuous Galerkin formulation that we're constructing. The important thing here is that when we do adaptivity, if we use central fluxes, you obtain basically not such a good error estimator, but if we do upwinding, you obtain an excellent error estimator. And actually, in all the meshes, it's very hard to distinguish this continuous formulation from an optimal parameter, an optimal SUPG or an optimal variational multiscale formulation with optimal parameters. So this is for p equal to 1. We can do something similar for p equal to 2. And all this is, as I mentioned before, is implemented in Phoenix. So it's a fairly standard simulation framework where you can construct continuous and discontinuous basis functions. And we use Phoenix just to handle the data structures, to know which function belongs to which element or interface of the elements and construct the jumps and all those operators. And basically, the optimality that I claim we have is basically in the sense that once you're in this regime, adding an extra degree of freedom around the boundary layer corresponds to the behavior of the system as if you're having a uniform mesh globally, adding the same number of degrees of freedom. So that's the optimality we think of. So these central fluxes would lead to something like this. So as you know, if you're doing continuous Galerkin, continuous formulations, even though they are stable, you can still have overshoots and undershoots. But for similar number of degrees of freedom, here what we report as, when we report number of degrees of freedom, it's the total number of degrees of freedom. It's both the continuous Galerkin mesh in which we solve plus the discontinuous Galerkin mesh in which we solve. So when we're reporting here degrees of freedom, we are counting both the whole problem. So the error representation, the error representative of the residual, and the solution, the continuous solution that we're looking for. And on roughly the same number of degrees of freedom, the upwinding formulation gives you a much sharper representation. So for example, to give you an idea of the meshes, the central fluxes would give you a mesh that is distributed this way, while the upwinding formulation would give you a mesh that looks like this. So remember that when we started, we didn't even see the boundary layer, the boundary data. So we were non-conforming in the boundary data, and we obtained a fairly good representation at this 30-second level of refinement, automatic refinement. We just chose that to have some resolution here, otherwise it becomes just a black line. So just to show that we don't need to have straight inner layers, we can have this discontinuous data, and again, our initial mesh will not see again the data, the distribution of the inflow data. And you can see that so this is a solution on the third mesh refinement. And I see that again, I didn't get the right link to the meshes. I'm sorry, these are not that easy to see here, but you see that already by the 5th level of refinement, this is a sufficiently good resolution, and then you can go crazy and let it refine 40 levels, and then you can have a very sharp representation of the interior layer all the way through the domain. So this is basically the goal we had in mind, and basically we're achieving it. So again, this is strictly advection problems. So now we put, again, advection skew to a mesh, but now we will add diffusivity. So the diffusivity is 10 to the -3, and we impose this discontinuous data. And again, the typical advection skew to a mesh problem that is done in the stabilized finite element community. And you can see that on a very coarse mesh, we represent a solution that looks a lot like SUPG. And then as you keep on refining and you start capturing the outflow under layer, you will have the outflow represented and the inner layer, and you get all the attributes of a solution that you wanted from an initial mesh that almost didn't see the data. We can do the rotating flow again with strong outflow boundary conditions. So it will have an outflow boundary layer here. And again, the initial mesh does not see the input data, so it's non-conforming to that point. But then the refinement strategy will pick up. By the third mesh, you already have somewhat of a representation of the flow. But then by the 5th mesh, we have a very good, 10th mesh, you have a very good representation. And by the 40th level of refinement, you have a representation of the boundary layer, representation of the inner flow, inner layer, and the input data gets properly refined. So what I'm trying to say is that the formulation works robustly. And we have tried several PDEs. Right now, I'm focusing on pure advection and advection diffusion, which is this case. So we can do it in 3D. Similarly, what we'll do is we'll start with a mesh that will not even see the initial data. So the data is basically a non-zero inflow boundary condition on a circle around the center of one face, and the flow rotates in this direction. And then it's pure advection. So the third mesh, already you can see some of the features of the flow, but already by the 5th mesh, you have a fairly good representation of the solution. And then you can just let it go, and then by the 50th level of refinement, you have a very precise representation of the inner layer all through the domain, which is the original problem I showed you. And then we can do more three-dimensional flows, which is this swirling flow, and I'm just going to show you some cuts. So this is the mesh distribution at the 32nd level of refinement, something along those lines, 30th. This is a contour solution. This is the analytic solution because this is just pure advection, so we can compute the pure advection flow. This is the solution that we obtain numerically. And these are cuts of the solution at some different planes. The meshes that you obtain, this is the inflow mesh, this is the outflow mesh. And these are the convergence for these refinements, for adaptive refinements for P1 and P2, measuring the error in this DG norm. So as I mentioned before, when you do these stable discretization, stabilized finite elements, what you obtain are solutions that can have overshoots and undershoots. This is SUPG's formulation with weak imposition of boundary conditions. This is our formulation. And actually, if I take different cuts, you cannot tell them apart, as I mentioned. For a given mesh, the solution that you obtain and the solution that SUPG would give you with optimal coefficients are indistinguishable. But as I mentioned before, if you have to go with stabilized techniques to a new problem, you have to develop the theory again. And we're basically building on the DG formulation for a particular PDE and just use that blindly. So the next part of the talk will be we're trying to develop techniques that allow us to remove these overshoots and undershoots. So what we'll do is use this stabilized residual minimization technique, but we want to remove these overshoots and undershoots and go to a solution that weakly imposes the constraints on the data, the minimum and maximum constraints on the data. And the way we do it is we use a Nietzsche method, which becomes a nonlinear penalization. So we are hacking an idea of Burman and Ern, who did it as a modification of a way of doing imposition of elastoplastic flow rules by Nietzsche method. So what they're doing is we're imposing constraints by a global Nietzsche penalization. The way the formulation looks is basically, I'm introducing a little bit of notation. We call this operator A, and you'll see it in a second that I use it in that context. This problem will have the residual minimization technique I showed you before, which is basically, given a formulation, you can postulate this saddle point problem in the DG norm for, again, the representation of a residual, the Galerkin orthogonality weakly. And U, as the way we think of it, is always simply the continuous space for a particular DG formulation. That's the way we construct our meshes. So the formulation looks as follows. We'll have the error representation plus a penalty term, and then we impose on the tangent for this nonlinear term, the constraint of Galerkin's orthogonality. And we just iterate on this method. Details on the formulation, how we solve the system, how we impose the nonlinear constraints and all that are going to be explained later in this afternoon by Roberto Sier, a student in the group, in 5:30, room 205. Anyway, so this is the formulation, and the way the solutions look is basically we want to, again, solve advection skew to a mesh. And with this penalization, you see, and I blatantly stole the slides from Roberto. I had my own slides, but he showed me over the weekend his presentation, and I thought the slides were excellent, so I just took them over and put them here. So this afternoon, if you come, you'll see some of the numerical results are going to be, the numerical results are going to be the same. He's going to show more about the formulation, and the difference is going to be the details, how this is done. But basically, you can see that with this penalization, you get the blue line, which is basically removes all the undershoots and overshoots in different cuts for a mesh of 10 by 10 and 50 by 50. And more importantly, what we can do is solve these kind of flows where we can remove the oscillations in any of the cuts of the domain, but more importantly, we don't affect the convergence rates. So by introducing this nonlinear penalization, when we solve the system, we basically retain the same kind of convergence rates that we had when we have the oscillations, which means that with penalty, you get the continuous lines, and without penalization, which is the original formulation, you obtain the dotted lines. And once you are sufficiently refined, you cannot distinguish. Actually, once you are in these levels of refinement, you can put a traditional continuous Galerkin formulation, and the solution you will obtain there is excellent, because we drive the mesh to be an excellent mesh, even if you put a continuous Galerkin formulation. And to give you an idea of the extra cost, we solve these final meshes at basically an order of magnitude more expensive than Galerkin on that mesh would cost. So we're not saying that this is going to be cheap. That's why a lot of our effort in the future will be developing better solvers. But it's robust, and you can apply it to any problem. That's basically the sales pitch right now. And since it's a symmetric positive definite system, everything we have thrown at it works really, really well. Even when we give the matrices to PETSI and ask it to give us an estimate of the condition number, and the condition number will be terrible, 10 to the 100 or 200. But a few iterations converge, which is surprising. That's why we need to understand better why we obtain such a behavior. The next topic I want to talk about is basically goal-oriented adaptivity, where the point is that we started with this problem, which is, in this context, we'll call it the direct problem, which is the original problem we were solving. We'll formulate this this solve point problem to solve, which is exactly the same as we had before. And now the dual problem simply becomes computing the adjoint problem of the original problem. And then what we want to do is drive the problem by G, which is a measure of the quantity of interest we have in mind. And at the discrete level, basically what that means is that we put the first equation now becomes a constraint. Before, the constraint was that the residual had to be orthogonal to your continuous space. Now, in this context, the constraint is the first equation, and you are driving the system in the second equation. So in the previous system, in the direct problem, epsilon is an error representation. In this dual problem, which letter? Omega, is not an error representation, is a solution representation, is what you're seeking. So what we have to do is post-process this system to obtain an error representation. And the way we do it is we use the fact that you can think of it, now we can test on a larger space and measure the error on a larger space, or you can use dual arguments. And since this problem is solving a problem in the dual of a continuous space, which is a subspace of VH, when you look at this problem and you're measuring the error in VH, since the dual of that space is smaller, you can have an error representation. And this simply becomes once you have the solution to this problem, you come and do one more iteration of the inverse of G to compute the error estimate. And then it's fairly easy to compute that the paper we submitted last week, I would say, proves that this estimate is true, which is that epsilon controls the error on your distance between your solution, the solution to the PDE and your continuous finite element discretization. This one is something we're working on. I believe it's mostly complete, but basically assuming that you have these two, it's fairly easy to prove that the error in the goal is going to be bounded by this inner product, and then since you have the bound on the inner product, then just taking the Schwarz inequality allows you to have that estimate. But bottom line is that once you have epsilon and eta, you take just inner products of them, and you can drive the error representation. So we'll take the goal, that is taking an average of a solution in a certain domain. And then in addition, we'll test another goal, which gives us better, tighter bounds, which measures the quantity of interest, the original average of U, scaled by the error representation. And what happens is that local cancellations that happen in the error in this equation in the first one are removed, and this one gives us tighter error bounds, that's all. So the local error representation that we use is just the DG measure of your error in your element of the inner product or just the products of the norms. And the goal, the measure of the error globally is basically the sum of the elemental errors. And the way we drive our automatic mesh refinement is we want the elemental contributions to be reduced every time we discretize the mesh. We start with a classical problem that Tinsley Oden and Serge Prudhomme did almost 20 years ago, which is this Laplace problem with an exponential driving the problem. This is one mesh we obtain at the level 16th of refinement. And these are the reductions on the difference of U minus UH over the domain that you want, not the actual goals, but rather method 1 and method 2 gives you comparable meshes. In this context, in the elliptic problem, the method 2, the one that we scale by the error representation, gives us a better solution, but in other problems, that's not the case. They are comparable. So the message here is that these two methods will give you comparable solutions, although once you want to control your quantity of interest, this bound, the original one, is worse, it's less tight than this one. So you can have more confidence than once you multiply by the residual that you're on a tighter bound. Similarly, you can go and solve advection diffusion. Same formulations as I showed you before. You do the dual, you have a unique solution, you drive that, you represent the error by solving one extra iteration. In this problem, we're trying to measure the error here, given that we have inflow advection going in that direction. And as I mentioned before, now it's hard to distinguish between the two methods. But what will happen is that, Oh, by the way, since we are driving goal-oriented error representation, the solution is not excellent. It's just good enough to drive the difference between the solution and your discrete solution in this space only. And you see again that this second one that is scaled by the residual is much tighter representation and has the right slopes, while these ones don't have the right slopes. That's not something we have a good explanation for, but that's the state of the art. And then we just can do pure advection. Same problem, same formulations. We have discontinuous data, and I should have a plot here of the final result. I don't know why now I don't have it. So Alessandro, you were asking me if I had all my pictures in the right place. No, sorry. So the problem is this pure advection with the flow rotating, and we're trying to determine the error, minimize the error in this domain, basically between 0.1 and the outflow here. To capture the solution here, you can see again that once you are advection dominated, the distinctions between the weighted residual and not are basically indistinguishable on the quantity on the U minus UH measure, but the goal, this one has a much tighter representation of the goal than this one, and actually has the better slope representation. So that's basically why we're going with this one, this weighted residual one. So conclusions. We have built a formulation that borrows from the theory of discontinuous Galerkin and allows us to represent on given meshes good, stable solutions that use continuous representations of a solution, so stabilized continuous Galerkin frameworks. The cost to pay is that we solve a global system that is larger than DG, but is proportional to that cost, order of magnitude DG cost. We have applied it to hyperbolic and elliptic problems. We also have space-time formulations, so we know that it also works for space-time and parabolic problems. It's very simple to implement. That's why we use Phoenix, such that you have all the hassles of using a framework from someone else. You have to learn their data structures and all that. But then the maintenance and testing and all that is taken care of by them. The formulation is always well posed. The error estimate can guide adaptivity. And right now, the formulation that we use basically has roughly linear cost. Every time we double the number of degrees of freedom, the solution of the next level is twice as the previous level, from a mesh that doesn't even see the boundary data to 50 levels of refinement, where some of the elements were refined 30 times. And some of the mesh will have roughly size 1/2, which is the original mesh size you had in one corner of the domain. Everything is efficiently implemented in Phoenix. Positivity preserving, these nonlinear constraints, goal-oriented adaptivity. And then Eirik Balseth will be talking about an alternative formulation where we based everything on local representations of the error, where here we lost robustness, but it's extremely efficient. So if you want more details, you can look at Eirik's presentation this afternoon. And we have initial results and some of the theory behind the application of these methods for nonlinear problems, because here, the nonlinear problem I showed you is basically a constraint applied to a linear problem. So the proof of convergence and all that relies heavily on the fact that the linear problem has a unique solution. Once you go to nonlinear problems, then a lot of the bets are off, so the problem there is harder. So then you have to specify very, very particularly the class of nonlinear problem you're looking into. We have space-time formulation working, but given my stubbornness, I would really want to develop a method that allows us to do something that is akin to a method of lines. Because in practice, meshing in 3D is hard enough. Meshing in 4D, I don't think it's going to be feasible. So in the near future, unless you do always tensor product in space and time. So basically, that's why that's something we still are looking into. And we already have a working implementation in DL2. And I'm very keen on having an implementation working in FEMPAR, the work developed by Javier Príncipe and Santi Badia in Barcelona, although Santi now moved to Monash in Australia, so now he's closer. Anyway, this is what I wanted to talk today about, so thank you.